Hello, everyone. Um, our next topic is distances between lines in 3 space. So to help you visualize what's going on, kind of imagine you had a dog sitting on your lawn, okay, and you're going to throw a frisbee for him, okay, and it's going to take a path in front of that dog. So if the dog wants to save himself some energy, okay, he would want to jump for it or go in the most direct route to the frisbee. So figuring out where the line is, okay, he would want the perpendicular distance from himself to the path of the frisbee, wherever that might be. And you kind of wait for it and jump at the appropriate time. Okay, and again, try to imagine this happening outside, right, in 3 dimensions. I know it looks really flat on the screen, but that's kind of what we're talking about, right? The dog is kind of like a point, and the path of the frisbee is a line. And I'd like to know what's the shortest distance between the point and the line, which will then build up to the distance between 2 lines. I have 2 separate paths. Okay, but this is the concept we're going to start with: is how do I figure out the distance between a point and a line in 3 dimensional space? Okay, so we're going to run through the technique and then do an example. So my givens are going to be a point in space, okay, and a line. Okay, I would like to know what the perpendicular distance is between the point and the line. Okay, and if I knew where it struck the line, that would be really easy because I could just figure out the length of that vector running from A straight down. But I don't know for sure. Right? When I have my equation of a line, I do know a point, but it might not be that one. Right? My point might be over here somewhere. Okay, so let's call that X. So here's the general idea of the technique. First, I'm going to connect a line, or should I say a vector, from A to X. That's created a right angle triangle for me. So I can figure out this part, okay, by projecting AX onto the line. So this is the projection of AX. And for the moment, I'm going to put an L here for line. Okay, and then with those things together, right, I could know the length of this. Okay, I call that's my C. If I know the length of this, that's A. And now I just need the length of that. Okay, and that would be Pythagorean. So those are basically the steps. And you did have a question that was sort of along this idea on your last assignment. Okay, so the steps are: we create the vector AX from the point A to the line. We're going to project AX onto the line, okay, and then get the length of both AX and its projection, and then use Pythagorean theorem to figure that all out. Now, in the end game here, we only need lengths, so it's going to provide a little bit of a shortcut that I'm going to show you during the example here. Okay, but we'll start working through our steps. Okay, so step one, okay, is I need the vector running from A to X. Okay, so here's my point A. This here is going to be my point X. Okay, so when I subtract those, I'm going to get -1, -1, and 2. Okay. And since I'm going to need it later anyway, I'm going to stop for a minute and figure out what the magnitude of AX is, right? So that is the square root of -1 squared plus -1 squared plus 2 squared. So that is the square root of 6. Okay, and I'm going to leave it like that in exact form because later on that'll be easy to work with. Okay, now step 2 was to figure out the projection. So I want the projection of AX onto my line. Now when I say the line, I really just mean the projection vector here. Sorry, the direction vector. Okay, that's the part I'm really concerned with. Okay, and it's been a while since we've called it this, but we did call this M when we first set up a line. So this is the projection of AX onto vector M. Okay, let's review how we do that. Okay, so in the Cartesian form here, I would do ax dot m over m dot m times m. Okay, now this is where I'm going to take a moment to set up my shortcut here. Okay. I really want the magnitude, right? Eventually I want the length, just like I had before. So I just want the magnitude of this projection, which means I need to take the magnitude of everything I see here. Okay. Using the properties of dot product, okay, on the bottom there I have m dot m, which is the same as magnitude of m squared times magnitude of m. So I can do a little cancellation here. And this is really all I need to do. I have ax dot m, and I guess I still need magnitude there. Okay. And then I need to be over the magnitude of m. So this is my simplified formula for this step. Okay, so I'm just going to highlight that here because I really only need the length of my projection. This is what I have to do. The magnitude of the dot product over the magnitude of m. Okay, so now let's fill that in and we'll be ready to go here. So magnitude of my vector ax was -1, -1, 2, and my vector m was 3, 4, 1. Over the magnitude of m, so the square root of 3 squared plus 4 squared plus 1. Okay, so on the top I'm going to get -1 times 3 is -3, -4, 2, so I've got magnitude of -5 over square root of 26. So that is equal to 5 over root 26. Okay, again, for the moment, I'm just going to leave it like that. Okay, my final step is to run Pythagorean theorem, because now I have both the lengths. So 3 Pythagorean theorem. Okay, so to help me keep straight what I'm doing here, I'm just going to quickly redraw what we did. Okay, there was my line. Okay, I had my point A. Okay, and I had my point X. We figured out the length of AX. Okay, I'm going to now call this point that I don't know P. So I can just put some labels on here. Okay, so Pythagorean theorem says that the length of a to x squared is equal to the length of p to x squared plus the length of a to p squared. Okay, what I'm looking for is this one. Okay, the magnitude of a to x squared. So we worked out that magnitude of a to x was the square root of 6. So we're going to square that. Okay, the magnitude of p to x, that was my projection. Okay, so that is 5 over root 26, and that's squared, plus magnitude of a to p squared. And now I just have to solve this for the magnitude of a to p. So I have 6 equals 25 over 26 plus magnitude of AP squared. Okay, when I bring that over, let's see, I've got 6 minus 25 over 26. So I'm going to get 131 over 26 is equal to magnitude of a to p squared. Okay, so the square root of that is equal to the length of a to p. Okay, and that is approximately 2.24. Okay, so that means that the distance between that point and the line is about 2.24 units. Example 2, determine the distance between these two lines. Okay, so we need to jump to lines, but okay, having a quick look. Okay, I have the same direction vector. Okay, I mean, it's a scalar multiple, 1, but it's same direction. These are parallel lines. Okay. So basically, the technique here is exactly the same, right? I know a point on the first line. I could call that A. I know a point on the second line. I can call that X. And then everything else just follows through, right? I'll figure out A to X. Okay. Then I'll get the projection. There's my point P, and we'll run through the same thing again. So from here, it's the same steps. We'll try to run through them a little bit more quickly here. Okay, but there's step 1. So A to X. Let's call this my point A, and this my point X. Okay, so I'm going to get -3, +11, and 4 as my vector. Okay, and again, while I'm here, we'll just figure out what the magnitude is. So the magnitude of A to X is, let's see, I would have, this is going to be 121, this is a 9, so that's 130 and 16. Okay, so square root of 146 is the magnitude of that vector. Okay, step 2. Now that I know my shortcut formula, I can go right to it. So the magnitude of the projection of A to X onto the direction vector is equal to the magnitude of AX dotted with the direction vector over the magnitude of my direction vector. Okay, so again, I'm not going to write this all out. I'm trying to save a little time here. So let's see, AX was -3, 11, 4. Okay, my direction vector is 3, 0, 2. So -3 times 3 is -9. Let's see, -9, 0 times 11, that's gone. So +0 +8. So it's going to be magnitude of -1. Okay, over 3 squared, which is 9, plus 0 squared, plus 4, 2 squared, so 4, so over 13. Okay, so that's over the square root of 13. And so I have 1 over root 13. Okay, final step. And this is using the Pythagorean theorem. So 3. Okay, magnitude of AX squared equals magnitude of XP squared. I think I called it PX last time, but same thing. And magnitude of A to P squared. Okay, so we had magnitude of 146. So I'm going to square that. And I have 1 over root 13. I'm going to square that. Plus AP squared. All right, so I have 146 equals 1/13 plus magnitude of AP squared. Okay, so 146 minus 1 over 13 is equal to 1897 over 13. magnitude of AP squared. So the square root of 1897 over 13 is equal to the magnitude of AP. And that's a little over 12. 12.08 is the magnitude of AP. Approximately. Okay, there we go. Okay, so that was nice, right? Because the lines were parallel. So we just adapted the same technique for parallel lines. Okay. The other case, right, for a distance is we could have skew lines. Okay, this is a little bit different, okay, because I now need perpendicular distance to go both ways. Okay, again, if I was in the classroom, I'd hold up some sticks and I'd show this to you. So it's going to be a little hard to describe. But the basic idea is I need something that is perpendicular distance going both ways. So when I figure out this distance, if it's really the shortest distance, it's going to be perpendicular to this line and perpendicular to that line. So this technique is a little bit different because I do know a way to find something perpendicular to two different lines at once. Okay, if I pretended for a second that those two lines overlapped and hit each other, right, I can figure out the perpendicular by finding the cross product. Okay, once I know that, I can simply project AX directly onto that vector. Okay, so that's what I'm going to do instead with skew lines. Okay, I'm going to find the projection onto the normal. Okay, so those are basically the steps here. We're going to find a common normal, and that is using cross product. Okay, now we're going to project AX onto that normal. Okay, so let's run one through to show how it works out. Okay, determine the distance between these two lines. So our first step is we're going to get that common normal. Okay. So 1. The common normal is the cross product of the two direction vectors. So I have 1, 1, 1 crossed with 2, -1, 1. Okay, so let's quickly review that. 1, 1, 1, 1, 1, 1. Now I made this example nice and easy for the setup. 2, -1, 1. Okay, so scratch that one out. Okay, so I have 1 times 1. I mean minus negative, so that's 2. 2 take away 1 is 1. And -1 take away 2 is -3. Okay, that is my common normal vector. Okay, step 2. Let's figure out AX. So if this is my A and this is my X, then that vector would be -1, 1, and 0. Okay, third step is to project it. And again, I only really want the magnitude of that projection because I want the length between the two lines. So I can use my little shortcut. So the magnitude of the projection of AX into the common normal, okay, is going to be equal to AX dotted with my normal over the magnitude of the normal. Okay, so AX was -1, 1, 0, dotted with 2, 1, -3. And that is all over the magnitude of 2, 1, -3. Okay, so I get -2 plus 1 plus 0. So that's magnitude of -1 over 2 squared is 4, 2 squared is 9, 1, so over 14. So that's 1 over root 14, which is approximately 0.27 units apart. Okay. So that's the technique between skew lines. Okay. And just as a side note, okay, that means it is possible, right, that this could come out to 0. Okay. If the two lines actually intersect, then you should get 0 as your final answer down here. Okay. Some food for thought there. All right. Okay. So thanks for watching. Here's the practice. Okay. To get enough practice questions, okay, I have an additional handout here that you'll find on the website. Okay, and there's a few more questions on there. Okay, however, a little word of warning here. There's a couple questions on here that use a slight twist on the line format. So I'll just do a quick example of that for you. So for example, in question 8 here, they've got this format with x minus 2, y, z plus 1, okay, for line 1. Okay, so two things to note, they're using round brackets instead of square. Okay, and what's happening here, so I copied it over here, is they just moved the position vector, the point, to the other side of the equation. Okay, right, so we would write this out first with square brackets. Y, z plus 1. Okay, equals r 3, 0, -2. So next, I'm going to separate the point. Okay, so I have x, y, z plus -2, 0, and 1 equals r 3, 0, -2. Okay, I hope you can see what's happening there. They just took this point and brought it into this and made it a single piece. Okay, so last step in separating this would be to bring this point to the other side of the equation. Okay, but it's plus now, so when I bring it over, it would be subtract equals negative of -2, 0, 1 plus r 3, 0, -2. Okay, of course, but I don't have to leave that negative hanging there. That just changes the direction of this vector. So that is a long way of saying that weird little equation is actually this. Okay, that's the equation of that line. Okay, I think there's only one other where you have to make that conversion, and that's it. Okay, so if it's driving me crazy, just do number 8. And when you see the other one, maybe not worry about it. Okay, but yeah, there should be lots of practice there to practice those skills. Okay, thanks for watching, and hope you join in for the next video when it arrives.